Hi guys, welcome back. This is part 3 of my video series for exam 3. Today I'll be coding out the finite differencing stream, and here, let me title this is be finite, and it's going to be unstable finite. Okay. So basically, what this is going to be doing, I'm going to be coding in the equation that we had last time. And right now I'm importing numpty as np because that's what we use to get all of our goodies from. So plotly, and then plotly is what we use to graph the equation, and that's going to be import make subplots. Good. Okay, so now we need to put in the number of increments we're going to have. So that's going to be number of increments is going to be equal to 50. Our time increment is going to be equal to 2000. And then alpha is going to be equal to 1.0. Our delta x is going to be equal to 1.0 as well. And then our delta t is going to be equal to 0.5. So now our R value is what we found, is basically what the first part of the equation, if you remember from the last video, it was it's just alpha delta t over delta x squared. Okay. Yeah. So it's going to be R is going to be equal to alpha times delta t divided by delta x squared. Okay. So, and then our t value is going to be running through the entire bar here. So that's going to be np dot full number of increments. So our number of increments is going to be 50, and then through 20. We're just going to run through 20 right now. Notice how I'm putting decimals is because if you don't put decimals in this code, it does not run right for some reason. I'm not exactly sure why, but it just doesn't follow through completely, and it makes it messy. So our first index is going to be equal to 0. That's the length of the bar, is 50 meters. So, and then our previous one is going to be -1. So the end of the graph is going to be equal to 80. So that. And then so from here we can make our subplots. Yeah, make sure everything's good so far. Yep. Okay, so when we make our subplots, it's going to be equal to fig equal make subplots, and then we're just going to have rows. That's going to be equal to 1, and our columns are going to be equal to 1. All right, and then from here we're going to do our where am I going to go with this? So from here, I could show here. Right now, I'm going to show what t is, so we get an idea what that's going to be. So see how t goes through all these values down here? That's what the graph is going to be graphing right now. But we don't want it to graph just the t value, so we have to put it in our equation. So when we do that, we're going to do for I in range, and that's going to be through 1, so the first index, and then plus our number of increments, and that's going to be +1, okay? And then from here, and then from our number of increments, we're going to be doing our t. So this is going to be the forward positioning. So t is 1, and then colon, and then -1. So that's our forward position scheme. We tried this last time, so I'm just putting in that equation. I'm looking at it right now. It's on our whiteboard. So from here, it's going to be t, and then it's going to be our t plus 1. I mean, yeah, our time now. So our time now. So or the it's going to be 1. So -1 colon -1, and then it's going to be plus r. So our R value, so our alpha times delta t times over delta t squared. So So times that, and then everything in the parentheses that we had last time, so it's just going to be t. Now we're just going to do it in code form, so it's just 2 delta, and that's going to be the forward, and then minus the current time right now times 2t, and then that's going to be 1 negative 1, and then we're going to have plus t delta 2 minus 2. Okay, so hopefully when I graph this, it all works out the first time correctly. So now we're going to run this through if. So our if I is going to be percentage, so it's going to be multiplied through. So it's going to basically break up all these little lines for us. That's our goal here, so we can see every basically time, every second, millisecond even really, when it's running through the bar, like the heat diffusion. It's really cool actually, think about it. So x is going to be equal to x, and then y is going to be equal to t. Oh, I forgot to add our I forgot to add our scatter plot here. The first scatter plot actually. Fig add so scatter, and then that's going to be x is equal to x, and then y is equal to t, and we have to give it a name. So our name, we can name it initial conditions. Okay, so back down here, y equal to t, and then we're going to have the mode now. So mode, basically you can put bar graph, you can put bar graph or lines. We want lines, so mode is going to be equal to lines. And then our name, so we're just going to f, and then it's going to print our I value, basically what we're doing here. So f, then our number of iterations through here. And then we're going to hit fig. We're going to hit fig.show. So hopefully this all works. Okay, we have an error. So float object is not callable. So that means something up here is not working correctly. Let me look. So our for I in range 1 n plus 1, and then our t times the parentheses 2t, and then our minus 2t is going to be 1, negative 1, and then plus the t, and then our previous time. So that looks correct, but something's not right. T1, but when it says not callable, what? For I in range 1 n number of units plus 1. Wait, does this need to be? No. Okay, let's see here, guys. So our 2 is going to be here. Our negative 2 is going to be there. What's the issue? Went through there. Our t negative 1, and then what is wrong here? 20, t equals 0, t equals 9. I don't want that to x, 0.5, 0.5. I don't want alpha. So fig equal make subplots, rows, columns equal 1. Name is initial conditions, and then for I in range 1, a number of increments plus 1, that's all correct. If I is percent, what? Not callable. What? Not callable. All right, hold on. Our t increments. Did the decimal throw it off here? Wait a second. I think it might be these. These might be actually throwing it off. Let's see here. Flow object is not callable. Flow object is not callable. Like going through everything, make sure everything's cleared up. np.full. np.full. Number of increments is through 20. I'm pretty sure a decimal is supposed to be there. I don't know. And then TT. Oh, duh. I see the issue now. Our x value is not there. Yeah, so this scatter plot won't work if we don't have an x value. So all you have to do is our np a arrange, and then that's going to be our number of increments times our dx. See what happens now. Hopefully that's the issue. I think it is. What the? Okay, so our graph is not supposed to look like that. That is very messed up. Fig ag scatter, x equal x, y equal t, mode equal lines, n equal f of I. Let's see what the issue is now, guys. At least we have a graph this time, so that's better than last time. So, you know, there has to be an issue somewhere. We have to fix it. See, this is my favorite part of coding. It's like a scavenger hunt. Like, where did we go wrong? So x equal np dot number of range increments to the x 20, 50, 80. All right, let's see here. I'm pretty sure. I don't think it's something. Okay, I think it might be. Honestly, this might be turned off, like these parentheses, but I'm not sure. Let's see here. It was. Sweet. All right, yeah, okay, so this is the graph we want, and as you can see, it goes 0 is at 50, and then it all the way goes up to x. So now I have to show you why this is unstable, and it's very easy to show why it's unstable, actually. So our delta t is at 0.5. If we change this to 0.6, watch what happens to the whole graph, especially watch what happens to the y-axis. See, look at that. We have 1 to the 289th. That means it's hotter than the sun, hotter than 10 to the 10 suns, basically. It's insanely hot. And that's just off changing one value. This is why it's unstable. Because if you have a different delta t come in, like say like, oh, let's have a 0.4 now. See what happens. This is why this is called unstable finite differentiation. All right, this one isn't as bad when we have a 0.4. You can see the y-axis dropped a little bit too, like the lines did here. Like let's keep looking at 12. We'll keep on looking at 12. So we'll drop it to 3 now. So see, it dropped more. It dropped more now. Now let's see what happens if we increase it to say, I don't know, 0.9. We have encountered an error. But yeah, see, like insanely hot, and it just doesn't make sense. Like here's our 13 or 12, which whenever when we were looking at before, it's all messed up now. So And we got this error, runtime overflow encountered an add, runtime overflow multiply. So yeah, change this back to a 0.5. So, and now we're good with the video now. So what I have to do is I'll show you guys, so the next 3 videos, I have to derive this derive a stability. It's called von Neumann stability analysis equation. And then we're going to be doing a Crink-Nicholson equation too, which that would be implemented in the code and the von Neumann. But first I have to derive the von Neumann, I think, for you guys. I'm pretty sure. Yeah, I have to derive the von Neumann. And then from there, we're going to come back here again and we're going to try to fix this out. And honestly, I don't think it's not that hard to fix, but like the math behind it is pretty complicated, and it's a lot easier to show it on a whiteboard instead of just explain it through coding. Because even this math was like the R value was a little hard to find too. All right, well, welcome. I hope to see you for part 4. This is part 3. Let me just write, so my prof knows that this is part 3. Let's write it in the code right here. Part 3. All right. Thank you for coming today, and I hope to see you guys later so you can see how we fix this unstable finite stream and see how we can make it stable. All right. Bye, guys.